Yeah, so my name is Zach Asher. I want to talk about breakthroughs in autonomous winter driving. And this research that I'm going to present to you and hopefully just give you kind of a very broad overview of some of the things that are going on comes from, first and foremost, Western Michigan University, where I'm an associate professor of mechanical and aerospace engineering, and I also direct the Energy Efficient and Autonomous Vehicles, or EVE Lab. And also, this information comes from our startup company, Revision Autonomy, where I'm a co-founder and serve as business and technology director. There we go. Okay, so here's the broad overall agenda for this presentation. So there's two parts. There's sort of the Western Michigan University side, where I'll talk about my background, current projects, and past projects. And then we'll transition abruptly to the startup company work, which I think is very relevant for the conference, where I'll give a background of the company, our current projects, and future work here. So starting with the Western Michigan University side, we'll go ahead and jump right into it. I'm going to talk about my background and sort of how the EVE Lab came to be. So first, I lived my whole life in Colorado till I got this job at Western Michigan University. Got my bachelor's in mechanical engineering from Colorado State University and started doing research as an undergraduate researcher at that time. My master's at University of Colorado, Colorado Springs, doing aerospace stuff, actually. Also worked full-time in industry from 2009 to 2015, at first a big Department of Defense contractor and then at a small Department of Defense contractor. Went back to school, eventually got sick of the industry life for a PhD, where I focused on enabling predictive energy management in hybrid electric vehicles, brief postdoc at University of Michigan. And all of that finally led me to my tenure track, now have tenure at the university. All right, so when you start a new job as a tenure track faculty member, you have to decide what it is that you're going to research. What is the thing that you want to establish an impact in, right? And so initially I thought, well, I will approach any mechanical system where I can apply modeling, control, and optimization. So created this MCO lab, and was open to any funding opportunity, really. And soon learned that the state of Michigan provides lots of opportunities for autonomous vehicle research and development. So after 3 years, I sort of looked at where our funding was coming from. 70% of it was in autonomous vehicles, and 30% was from energy efficiency. And so we just decided, okay, if that's what we're successful in, that's what we should focus on. So we rebranded the lab to the Energy Efficient and Autonomous Vehicles Lab. Since 2018, we've received $4.2 million in funding across 14 different projects. And the lab is really applications focused, right? So that's not cheap. It's not theoretical, people sitting around writing on whiteboards. We have real cars. We're out driving on public roads, really trying to solve some of these problems. So far, we've had 6 PhD students, 4 have graduated, 7 master's students, 5 have graduated. We've launched this startup company, which focuses on autonomous vehicle perception for snow-covered roads. We piloted 2 autonomous shuttles on WMU's main campus. I'll talk about that briefly, and created 2 new 3-credit courses, autonomous vehicles and electric vehicles. So this is some of our facilities and equipment. So we have a fully instrumented 2019 Kia Niro hybrid electric vehicle, which has a drive kit, LiDAR, radar, GPS, Mobileye, computers, etc. We have a 2015 Kia Soul all-electric, same sort of setup. We have a low-speed shuttle, which is called an Arrigo Autopod. You can see that in the image there on the bottom. In total, it's about 300 square feet combined desk and equipment space. We have a chassis dyno, high-performance server, lift, and stuff like that. So these are really the tools that we need to address energy efficiency and automation problems. All right, so I want to cover our past projects relatively quickly and just sort of hit you with the basic high-level learnings from each of these projects. So first, I'm going to painfully summarize my entire PhD on one slide here. 4 major learnings. Number 1 is that there's 3 major research gaps stopping a real-world utilization, a realization of optimal energy management. We're focused, again, on applications. How do we actually realize some of the things from the academic literature? Second was that optimal control is robust to mispredictions. This is important for real-world operations. Nobody knew that at the time. All of these are supported by the citations shown here, which are available for free on the lab website. We also determined that optimal control can currently be used in modern vehicles, and critically, that sensing and artificial intelligence is a key technology for optimal energy management. All right, so I say optimal energy management. What does that mean? Well, really, the only thing that you should pay attention to here is the overall architecture of this, right? So this is the full system, and it's easy to remember the subsystems because they each start with P. So first is the perception subsystem, which allows the vehicle to perceive the environment around it, understanding the driving environment, where are the lanes, vehicles, traffic lights, stuff like that. If you have that information, you can then give it to the planning subsystem, where you make a plan for what to do. Should we slow down, speed up, change lanes, etc.? And then lastly, that plan has to then be actuated in the vehicle plant, right? So how do we actually achieve that using a vehicle? For this initial research, it was a Toyota Prius, right? And in this case, the end result is 10 to 20% improvements in fuel economy, which is good for establishing energy security and things like that. So of course, the Department of Energy was very interested in this research. So we got to expand it in a $1.5 million project where my old university was the lead, and I was co-PI through Western Michigan University. We collaborated with a national lab, the city of Fort Collins and Denver, and the Northern Colorado Clean Cities Coalition. And essentially, it just allowed us to expand the study. So we can now look at bigger data sets, incorporate traffic light status for the first time, use, fancier AI, if you will, in this case, specifically cutting-edge deep learning. The impact of traffic and optimized traffic flow was a big part of this study, and investigating citywide benefits. So briefly, I'm not going to go through all this, but just very briefly at a high level, there's 3 ways to improve fuel economy. Eco-driving, which is where you drive like a grandma, basically. No offense. Eco-routing is where you pick a route that uses less energy overall. And then optimal energy management, which is where you basically optimize how much energy is getting from a battery or an engine to the wheels. And there's 2 ways to do that, rules-based and optimization-based. And so we chose optimization-based for this project. And essentially taking those 3P subsystems and adding traffic management to this as well. So traffic management is important because you can improve travel time. And then, of course, all the other components are for improving energy efficiency. So looking at doing both. We collect a lot of vehicle signals, such as speed, acceleration, and throttle position from the CAN bus. Historical speed data was collected. ADAS stands for Advanced Driving Assistance Systems. Those are just products that are currently on modern vehicles. And we use those to find vehicles in front of us in the lane and things like that. We also got signal phase and timing information from City of Fort Collins traffic operations, and then segment speed information. So we sort of feed all that in. The optimal control is just done with model predictive control. It's basically just a recipe that you follow. And then the vehicle plant that we used for the simulation is this physics-based software called Autonomy. We collected 13 real-world drive cycles around these main roads in Fort Collins, Colorado. We created a traffic simulation of this environment in order to optimize for 2 different traffic scenarios. This is the important point, right? So the point is that if you incorporate traffic optimization and energy efficiency optimization, you get synergistic benefits. So you have improvements of travel time and energy efficiency that are better than doing either of them alone, all right? But we did this just for this 1 square corridor. And then if you look at the overall impacts to the city, it's relatively small. This is just 1 road segment. So what this means is that in order to keep going with this technology, you have to incorporate more roads and expand the scope of the optimization, et cetera. So this is very hard stuff to actually figure out, but we're making good progress. So I'll hit you with some of the sort of high-level insights here. First, as I mentioned, energy management and traffic management together has synergistic benefits. Model predictive control is implementable in the real world. Long short-term memory, or LSTM, deep neural networks provide the highest time series accuracy. And then critically, infrastructure data, such as traffic lights, is the most critical for prediction and control implementation. We're going to see this conclusion a couple of times. All right, moving on to the autonomous vehicle pilot. So we had 2 autonomous Arrigo autopods piloted on WMU's main campus. There's a local Michigan company that was the lead here in Western Michigan. Myself, we were the co-PI, and we worked with these other companies here. All I'll say about this right now is that we basically just obtained practical experience. What goes into the design of a pilot? What are some of the challenges? How do you design specifically for wheelchair users? These vehicles were picking up students with disabilities at the bus stop and driving them directly to the building where their classes are, and then collecting ridership survey data. How is that done? All right, so then this led into a second pilot where the scope is now getting bigger, right? So we had 4 cars on public roads at this point. FEV is a Michigan automotive tier 1 supplier. They were the lead, and we were co-PI. And the scope here was to pick up people at the Detroit airport and drop them off Detroit downtown. And so what we did is we split it into 2 phases. So you can see the green there. It's called teleoperations. That's just a fancy way of saying remote control. And so as soon as the car gets off the interstate at the airport, you basically have someone in a building somewhere that's remote driving the car, pick up passengers, gets it back on the interstate. Once it's on the interstate, then the car goes into autonomous mode. Once it gets off downtown, then someone's remote controlled driving again. So that was the concept, but ultimately we never got to the pilot phase due to COVID. So if you're wondering, okay, how do you design an autonomous phase on the interstate? Well, I'll tell you, just give me 2 minutes here. The main thing that you have to do is you have to fuse camera and radar detections. These are mature technologies that are low cost, that are on existing vehicles today. And so the challenge is getting good data from them and fusing it together so that you're confident in the detections. All right, so in the vehicle that we're in this image, it's called the Ego vehicle, which is labeled with that orange box. And we're trying to detect that black vehicle in front of us. And so from the schematic or diagram there, you can see we might get 3 different detections. We might be detecting some tree off to the side. Maybe there's a vehicle in the other lane that we don't necessarily care about. The detection we want is the car right in front of us. So we collected data along I-94 near Kalamazoo, Michigan. That image on the right is all the radar detections that you get. And so if you overlay where the actual lane is on that image, just using geometry, you get those red lines. Right, so just doing that much allows you to eliminate 99% of the detections. So the radar gives you 47,000 detections. You limit that based on the range of the lane. Next, you look at some detections over the course of 2 seconds. Right, so you might get 5 different detections over 2 seconds, and you filter that based on which detections are sort of moving forward with the vehicle and which ones are staying to the side and not moving forward with the vehicle. That allows you to eliminate the next 99%. So actually what you get in those 3 different colors there are the next 4 vehicles in front of you that you can't necessarily see as a human driver. So then the only thing left is you basically just fuse the camera detections with the radar detections. The blue dot is from a product called Mobileye. It's the leading standard for detecting vehicles and lanes. And then the orange dot is the radar. So you use these sort of off-the-shelf algorithms, if you will. They're called dbScan and Kalman filter. Tweak the parameters a little bit, and then lo and behold, you have those solid red detections to the right, and you're confident that that's the vehicle in front of you. So if you have that information and you have your lane lines, all you need to know is whether to speed up or slow down, and that's pretty much it. You've got an autonomous vehicle on the interstate. All right, so what did we learn from these pilots? First, we learned that autonomous electric shuttles have a viable use case that is economically feasible. So in the shuttle case, once you eliminate the driver, these become very cost-effective, of course. We also were surprised to find that university campus non-users are actually highly tolerant of sharing space with autonomous shuttles. I don't know if this is just because university students tend to be younger or open-minded or whatever, welcoming, I don't know, but they all were pretty happy having these shuttles driving around campus. We also learned that sensor fusion requires specific algorithms that can affect computational cost, and that autonomous vehicles can actually drastically increase energy use with all these computations that have to be running constantly. The one I've highlighted here says, autonomous vehicle operation in inclement weather is not feasible for current pilots. So this is something that we learned by collaborating with the current industry leaders at the time. We said, okay, it's a little bit cloudy out and maybe drizzling. Say, okay, cancel the pilot today. No cars are running. We're like, really? It doesn't seem like it's that big of a deal. They said, no, if there's any inclement weather whatsoever, shuttles don't run. So we thought that was pretty interesting. I'll circle back to that once I start talking about company stuff. All right, so lastly, on the university side, I just want to point out in-motion wireless power transfer, something that we've been kind of loosely involved in. This is a cool concept, if you haven't heard of it, where basically you take one lane on the interstate and you charge electric vehicles using these like supercapacitors and things like that. So it's really cool, right? If you have an electric car, you can charge it while you're driving. And this is really good for ensuring that electric vehicles don't need humongous batteries with rare minerals and stuff like that. Addresses range anxiety and leads to near-term semi-truck electrification. So if you're curious about this stuff, I'd point you towards Utah State University. They're kind of the leaders in this, and they're very friendly, and they like to collaborate and stuff like that. We collaborate on these two papers where, again, what we learned is that infrastructure is key, and coordinated infrastructure rollout can address challenging automotive problems. And so for us, with sort of the autonomous vehicle mindset, this was pretty interesting. We're thinking about this in different ways. All right, so we took all this learning and applied it to new projects. So I'll quickly cover these new projects, but they're sort of ongoing, so I don't have, high-level major conclusions to share on these yet. I'll just sort of introduce you to them. So the first one, again, a project funded by the U.S. Department of Energy, where we are tasked with improving autonomous vehicle energy efficiency without compromising performance. And that compromising performance is sort of a sticky point, right? Because I could take a bunch of sensors and computers out of the vehicle. Oh, look, it's more energy efficient. Is it actually going to crash now? I mean, you don't really want to try it and see if it crashes. All right, so you can't use number of accidents as a metric, so we needed to create a new metric. We use the principles of resilience engineering, which predicts how safe a system could be. So let me try to explain that. First, it's basically just a general systems level technique for addressing complex socio-technical systems. It requires you to assess 4 system components. You want to assess the system's ability to respond, learn, monitor, and anticipate. So one of the key things from that literature is what's called the resilience triangle. All right, so looking at the image on the left there, you've got some baseline functionality of a system. And again, this is a general systems technology, right? So you can apply it to anything. So they call this the nominal condition. What's the sort of normal operation point for some system? At some point, there's a deviation, and so that nominal condition or normal operating point slips, right? And if it keeps slipping, then you're on that blue arrow, and the system will completely fail. But if the system returns to that nominal operation fast, shown as the red kind of triangle there, the system is said to have high resilience. If it still eventually returns, but it's slow, it's said to have a low resilience. And so we took this concept and applied it to autonomous vehicles. So essentially, if you just measure the error, right? So pretend you're in a car, you're in the middle of the lane, and the car starts to move outside of the exact center of the lane, right? We call that cross-track error. So if that cross-track error starts increasing rapidly, you could say that that's a deviation from the normal condition, right? So that's what's going on in the image to the right. So you have this increase in error, if you like. And so how fast we get back to the center of the lane dictates the resilience. So it's one of these things that's like, it's easy once you've like kind of done it, but at the time, no one had ever done anything like this. And so it took us probably 2 years to figure all this stuff out. All right, so of course we ran a simulation here, so I can briefly explain this. In this case, we're traveling at 50 miles per hour or something like that, going around turns, and these are activities that we sort of take for granted in our daily lives while driving. But what happens in a system that is looking for lane lines, if it misses those lane lines and you're going 50 miles an hour around a turn, if it misses it for just a second or two, it can have disastrous consequences. Right, so that's what's happening. There's some shadow, or in general, we call that occlusion, which just means that the lane line's blocked. And so in the simulation, what we did is we're trying to mimic how cars currently operate. You can go buy a car, my car does this, it finds the lane lines, and if it loses them, then you have to take over control. So that's what we did. So we have the driver takeover, which is shown with that purple arrow, once it loses the lane line. Right, so if you sort of smooth that out, it looks just like the resilience triangle. So I only show you this just to convince you that we're able to actually measure the resilience. We're able to measure how safe these systems are without letting them operate in the real world and cause crashes and stuff like that. So what we found, that red bar, is our new sensors that are more energy efficient. So not only are they more energy efficient, but they provide more redundancy that leads to better resilience of an autonomous vehicle system. And additionally, resilience engineering allows us to share new requirements with automotive companies for how to design safer systems. So it's abbreviated there, but LCS is just a lane centering system. Some cars come with that you can buy today. And so we've designed the resilience engineering assessment allowed us to create some of these requirements to share with automotive companies. All right, so now that you're hopefully convinced that we can sort of use new sensors without adverse consequences, I'll walk you through some of these new sensors here. So there's 5 chip-enabled raised pavement markers. I'll talk about those a little bit later. Those are essentially just raised pavement markers that can communicate directly with the vehicle. I know there's some DOT folks in the room, so maybe you're familiar with these. If not, we have plenty of time for questions. And then we have radar retro reflectors, offloading through the cellular network, high definition maps or HD maps with real-time kinematics, which just means highly accurate GPS, and then weather sensors. So we're developing these sensors. TRL just means technology readiness level. Some are more mature than others. And so we want to improve the technology readiness level of each of these sensors for the autonomous vehicle application, and collaborating with Oak Ridge, DriveU, and the National Center for Atmospheric Research. So the key thing is that these sensors not only help with energy efficiency, but they also allow improvements in winter driving. All right, so with that, I'm going to make an abrupt transition to the Revision Autonomy company stuff. All right, because here, with some of our new projects, they're sort of closely tied with commercialization efforts through Revision Autonomy Incorporated. So it's really, kind of led by myself and Johan Fanas Rojas, trying to transition some of this university research into products that you can buy. So the 2 products that we're working on is new advanced driver assistance system software, ADAS software, which is just a catch-all term for low-level automation in current vehicles. And then we're working on commercializing these chip-enabled raised pavement markers. All right, so I showed you this overall agenda at the beginning of the presentation. We're now done with all the Western Michigan University stuff. So I'm going to talk about the background of the company, current projects, and future work. So what is the company? It's a startup software company founded in 2020 with the mission to increase safe driving in adverse and snowy weather conditions by creating software capable of guiding both autonomous and non-autonomous, just means ADAS, basically vehicles, during inclement weather. So there's been lots of projects that have led to the spin out of this company from the university. As I mentioned before, from running those pilots, we learned that there are no solutions for driving in inclement weather. So once we learned that in 2018, 2019, we sort of started to think about that. Okay, how could we solve this problem? We proposed something to the University Technology Development Fund to establish proof of concept. Once we found that it was sort of working, we then pursued what's called Innovation Core, which allowed us to talk with over 100 people in industry to understand, what are your needs? How would this improve your operations? What kind of prices would you be looking at paying? Things like that. And then from there, we got 2 Michigan Translational Research and Commercialization grants to continue to develop the technology and business model. And currently, we're funded under this Partnerships for Innovation, again, continuing the technology and business model development. All right, so my stats are a little bit different from that video in the beginning, but I'll try to explain how I got there. So first, I just want to point out that, of course, I think we're all aware of this. Car crashes are a top cause of non-natural death behind only drug overdose and suicide. So it's a major problem for young people. Every year, over 40,000 people lose their lives in the U.S. And I don't really have the heart to show, a video of an actual crash here. So instead, we've just got this peaceful, snowy road here. So from our colleagues at the National Center for Atmospheric Research, they did this study to sort of look at, okay, how many of these crashes occur on U.S. highways during inclement weather? And they found 21%. So this means over 5,300 fatalities, nearly 500,000 injuries, and billions of dollars lost due to U.S. highway inclement weather crashes. That money is lost from insurance claims, emergency services, damages, time delays, and more. All right, so why is this happening? We have solutions that are supposed to address this. I think I've hinted at this already, but for example, here's a lane centering system, and that's part of a family of advanced driving assistance system products. And these have been shown to significantly reduce crashes. And basically how they work is, this is an example of an output from Mobileye, which is the industry leader right now. It looks for the yellow lane on the left and the white lane on the right in that image. And what you get from the Mobileye are those two green lanes. Green means high certainty of detection. And GM, for example, buys Mobileye. They put it in their car. And when you see the lane keeping assist on your dashboard, that's what this is from. So when it sees high confidence detections, it shows that on your dashboard. And if you try to steer out of the lane, the car will correct you. Interestingly, if you look at the requirements for these products, it's written in the requirements that the system shall shut off if under anything other than beautiful sunny weather. So again, there's no solution for anything that can handle inclement weather. And so we were kind of, we heard about this from the autonomous vehicles case, but we're surprised by, the current modern vehicle case as well. So this is what we sought out to address. And in this example, if you were to drive on this snowy road, you might pay attention to the tire tracks, right? So you can sort of incorporate that information and still identify what we call the left and right side equivalent. And so that's basically what this technology does. This is technology that can be directly integrated into existing vehicle implementation. So for some OEMs that are more vertically integrated, we work with the computer vision development group to license the product. Horizontally integrated original equipment manufacturers might buy their full ADAS solution from a tier 1 supplier, so then we'd work with the tier 1 supplier. All right, so you might be wondering, okay, this is a hard problem. How come no one's done it, and how do you do it? Okay, so I don't know how much of an appetite you have for these kind of things, if you want to tune out for the next 3 minutes or not, but I'll explain. So this is the overall pipeline for how to do it. First, you have the data preparation pipeline. So of course, you go out, you strap a camera to the windshield of your car, you go out and you collect data. Some of that data is not necessarily going to be useful. It's not the right conditions, whatever. So you have to do a little bit of data selection there. And then you have to do data labeling. So in this case, we're showing the computer vision annotation tool, or CVAT, for finding, in this case, tire tracks. So you have to go through image by image and identify the tire tracks. This process is called finding the ground truth. So you want to know, what is the 100% correct answer? And the only way to get that is to have a human do it, basically. So you have to do this process, and there's a lot of tools out there that help you, that make this go faster. There's not really any way around that. Once you have the data labeled, then you need to do feature extraction. So first you have this image where the road might only be a small section of it, so you have to mask it. It's called a region of interest, or ROI mask. And then from that masked image, you then need to choose which features you care about. Sometimes you convert it to grayscale. Other times you use red, green, blue channels. You use pixel locations, et cetera. So you put that together into what's called a feature set. So in this study, we show the results for testing 4 different feature sets. You start at 0. It's a weird computer programming thing. Just ignore that. gray pixel XY locations, red, green, blue, et cetera. So you want to test all these features. All right, so then what you want to do is train your machine learning or artificial intelligence model. And so you give that machine learning model all of your different feature sets. You say, use these to then predict this output. And it's just a math equation, right? It's just sort of tuning the weights and biases. We understand, machine learning and artificial intelligence very well these days. You can sort of trace out all the math that's going on there. And so all it does is it just takes those feature sets as inputs and then gives you the output that you want. Once you have the machine learning model trained, you then want to evaluate its performance on a subsection of the data. Traditionally, people use accuracy, precision, recall, and F1 score. And it's just different ways of evaluating. It's called the confusion matrix: true positive, false positive, true negative, false negative. They all kind of give you the same thing. So what we actually propose is using intersection over union. So for example, if you are predicting that yellow square and you say, this is the region that's safe to drive in, but when you labeled it by hand, you said the blue square is actually the region that's safe to drive in. If you have an intersection over union of 0, then you failed, the car is going to crash. If you have an intersection over union of 1, you have perfect alignment, right? So it's sort of a more precise way to evaluate your effectiveness at accurate winter driving. All right, so again, that's the overall pipeline there. Hopefully that wasn't too bad. Okay, so you put all this together and you evaluate some results. Of course, here green means good. Up at the top of the list is an algorithm called random forest with feature set 1 giving the best mean intersection over union. But mean intersection over union isn't the whole metric that you care about. You also care about real-time speed. In other words, frames per second, right? You want a camera that's running at 35 frames per second, probably, so that you have lots of opportunities to make detections. And so real-time compute is an important aspect of this. So if you actually go down to the second best mean intersection over union, that one's running at 1,000 frames per second on a common laptop. So one might choose this decision tree model with this feature set, and that's how you design a product in this space. All right, so I want to talk about some of the different milestones from doing this. Starting back in 2021, that paper that I just overviewed is from 2021. So this is kind of the output from that if you follow that process. So in 2021, these were our milestones. Processing speed on a common computer, a common laptop of 35 frames per second. Look-ahead distance of 95 feet, and the road classification is just 2-lane arterials in Kalamazoo, Michigan. Arterial, if you're not familiar, is just, a common thoroughfare, basically like 35, 45 mile per hour roads. All right, so then in 2022, we were looking to up the ante. So we started working with our autonomous vehicle platform, the 2019 Kia Niro, and we have collaborators in at Eaton in Marshall, Michigan, which is about 45 minutes from us, and they have their own proving grounds. They like our university. They let us use it for free. We're very lucky. So we designed some test scenarios over there to test these in a safe environment. We use this Z2i stereo camera with a windshield mount, and these are some of the results for the Eaton test track. The key here is that we were collecting a lot more data at the test track, and hand labeling all of that was starting to become a big pain. So there was this new architecture that sort of came out around this time known as a UNet convolutional neural network, which is basically just a way to automatically label, and you're just using the whole image as inputs. And so that was sort of our big learning from 2022. We apply that and look at some of these accuracy metrics. There's a significant improvement across the board from using this new architecture. Now, of course, I said that runtime is important, and so you have to sort of monkey around with the architecture in order to get processing speeds that you like. All right, so then that leads me to what are we doing now? In 2023, it's still ongoing, of course. Our work is funded by that Partnerships for Innovation grant that I mentioned, but we also got an SBIR Phase 1, which was the first award directly to the company. So we're now all employees at the company. We get paychecks for the company now. So we're excited to be officially spun out. The number one thing that we're working on is verification. We want to have 95% ground truth accuracy over 1,000+ miles of data as sort of this big hurdle for our current product. And the second thing we're focused on is feature refinement. We need to know from people who might use this, what do you care about? What things should we focus on first? What is required here? What's the biggest pain point, et cetera? Should we focus on a solution that continues to work through intersections? Do you care about bridges and tunnels? Do you care about the active snowfall case, glare, misleading environmental information, et cetera? Those images are all examples of some of those different cases that we could address. It's just a matter of which one should we focus on first. We're also working on embedded hardware. We want to demonstrate functionality on a small computer that could be implemented in production vehicles. And then, of course, vehicle integration. We want some new physical vehicle demos and pilots. All right, so I'll show you, just this video here and kind of just talk about, of course, the main selling point, which I've hit on already, is there's no products that work in snow. Right, so that's what we're focused on. And even in this case, you can see that double yellow there pretty clearly, but every once in a while, there's a little chunk of snow that'll cover it, right? And that's enough to throw off the Mobileye, which, like I said, is the current industry leader. It just won't work in that situation. There's some other alternatives, such as the Comma 3 and some software companies like Comcar and Algolux. Those are just standard cameras there, so you have to have your own camera and then you use their software. None of these work in snow. All right, so of course, in this video, I'm showing that it does work in the case where there's snow on the lane line and no snow on the lane line, et cetera. So there's some other selling points here as well. Since we don't have hardware, there's a lower cost. It's easier to integrate software, the automotive companies have told us. And since we're focused very heavily on verification, the verification validation stage on the customer side should be much smoother. They've complained a lot about some of these other products. All right, so that's just sort of one example. I'll show you this video of another example as well. I don't know, I guess the point is just that it's not easy to do this, but it is possible. So the left side there is white lane lines. You've got a white truck passing by. There's white snow everywhere. But if you work on the algorithm, you can find those white lane lines. When you're turning, you want the lane lines to drop off. Then when you're back into a lane again, you want them to reappear. You don't want them to be affected by the windshield wipers. If there's snow covering the yellow lane lines, you still want that detection there and you want it to be robust. If the yellow lane line comes through entirely, you still want that to be there. On the right side, there's no lane line. It's just a pile of snow. But as drivers, we know how to handle that, so the software should be able to as well. And you can kind of see that. When it opens up on the right, where there's somewhere to turn on the right lane kind of expands. So as this continues to run, I'll keep walking you through some of the other finer points of this. So first is this term called operational design domain or ODD. It's sort of automotive jargon. It just means where specifically is this supposed to work? So in our case, we want to specifically state that what we're focused on is arterials and highways, right? Those are where these big important crashes are occurring. So that's what we want to try to address as soon as possible. We're not focused on residential roads, back roads, or parking lots. Additionally, with snow coverage, we wouldn't want to focus on a zero snow coverage scenario, right? As I said, there's already products out there that deal with that. But likewise, an entire, like a road that's covered in 6 inches of snow that no one has driven on, it's hard to even figure out what's going on in that scenario, and it's relatively unlikely. So we call that the full snow coverage case, and that's also something that we're not necessarily addressing at this point. So what we are addressing is everything in between. We call that light and medium snow coverage. As I mentioned, we're focused on verification, right? So we want a verification of 95% or more over 1,000 miles of data. We have about 1,100 miles of snowy weather data now. Only about 950 miles of that is stuff that we like and that makes sense here. So right now, our sort of end goal is 950 miles, and we're 35% of the way there, with verification of 90% accuracy relative to ground truth. And this doesn't mean that, it takes a week for each 10 miles or something like that. It's just little things that we didn't know when we were collecting the data in terms of calibration, for example. We found a couple folders in the data set where the camera was moved just slightly 2 inches to the left, and we didn't know that, right? So once we add in this 2-inch offset, now we have 100 more miles. That works just fine. So we anticipate wrapping this up fairly quickly, actually. By the end of fall, we're looking at having this 950 miles completed. All right, so that's the software product. I'll briefly talk about this chip-enabled raised pavement marker product, because this is something that automotive companies don't care about, right? They only care about the vehicle side. They don't care about infrastructure. But departments of transportation, for example, do care about infrastructure. And so this is something that we're also working on to address the problem of autonomous vehicles in winter driving. So essentially, if you don't know what a raised pavement marker is, it's that thing in the bottom left. It's this yellow square in here where, in this state where it snows, we have snow plowable versions of these, right? So obviously that one wouldn't survive a snow plow, but there are snow plowable versions. And essentially what we do is we just put a chip in that transmits the lane line information directly to the vehicle. So you don't need a camera, you don't need fancy algorithms and processing and all that stuff. You just receive the lane line information directly. And so the image to the right is showing an overlay of lane lines, but that's just conceptual, right? So imagine that chip-enabled raised pavement marker transmits you the lane line information. I know that I can overlay that on where the lane lines are supposed to be, and I'm showing that in the image, but you don't even need that step, right? If you know where the lane lines are, just pass it to the planning subsystem and you're good to go. And so that's kind of what we're thinking on this. All right, so quickly cover future work and then open it up for questions. So first I want to point out that the chip-enabled raised pavement marker proof of concept project, that's through Western Michigan University, and in 2024, we're required to disseminate our findings to departments of transportation and metropolitan transit authorities. So the ones that we have letters of support from are Michigan and Tennessee Department of Transportation, Michigan Office of Future Mobility and Electrification, these two MTAs, Kalamazoo and Grand Rapids, and then City of Chattanooga and Portage. So we're going to do some on-road demonstrations of these chip-enabled raised pavement markers and kind of show what the impact of that could be, costs, et cetera, so that DOTs can understand, how might we be able to invest in infrastructure that improves safety for driving in snow, as well as energy efficiency. Other things we're focused on is maybe some new autonomous vehicle pilots. As far as we know, there's been no pilot that previously addressed inclement weather. And so there's two opportunities to address this in Michigan. One is a Kalamazoo pilot. So we could have a shuttle that transports students and faculty from Western's main campus to engineering campus during the winter in the snow. And then we could also work with Michigan Department of Transportation. They want to fund an autonomous vehicle pilot at some of their state parks. A lot of their beautiful state parks are far up north. They get a lot of snow. And so that could be another great opportunity to showcase the technology, but also draw attention to the problem of driving in snow. In our case, we're a startup company and we require support from a big company, in this case, like at least 100K, so that's something that we're working on. We, of course, want to collect more snow data, so we'll continue to collect data around Kalamazoo arterials and highway, but this winter we're going to expand into collecting data in Grand Rapids, northern Michigan, and along I-25 in Colorado. We have hardware calibration and data storage process improvements that we're going to implement for this season's data collection, and we're also working on a development of a snow driving simulator, which currently doesn't exist. All right, so lastly, refining these commercial products. Again, in order to realize a major impact in safety and driving in snow, we need to release commercial products and make sure that this technology is available to the public. So this is sort of our main goal here. There's a phase 2 funding that I'm going to apply for that would fund us to focus on features needed to drive sales of this lane detection in snow software product. It requires $125K in matching funds from an external collaborator or investor, so I still have some time to figure that stuff out. And then we're applying for a phase 1 SBIR to work on the chip-enabled race pavement marker as well. So seeking opportunities for pilots and communications with DOTs and other stakeholders. So I've got a great team here. We're entirely focused on the company, but then of course regularly collaborate with the EVE Lab at Western Michigan University. If you don't remember anything at all from this presentation, I want you to remember just 2 simple points, okay? So number 1, automated winter driving solutions are transitioning out of the university. We are at that point now. It's been ongoing at the university for a couple years, but we are now trying to move it out of the university and get this real world impact. Number 2, look for initial pilots and commercial products being available soon. So my name is Zach Asher on both the university and startup company side. So I'd be happy to answer any questions at all that you have. Thanks.
All right, we've got time for 2 questions.
Zach, fascinating information. Just real quick, use your crystal ball. Where are we with automated vehicles in 5 to 10 years? What does it look like?
Well, so I have kind of a biased opinion here. So let me see if I can, convince you of this. We've spent, as a whole, billions of dollars on this technology, right? We've been working on it seriously at the funding levels in the billions for at least a decade. And yet we don't really have anything, right? You hear about, some crazy stories about people putting cones on Waymo and cruise vehicles in San Francisco and stuff like that. But it's hard to imagine, okay, when is this actually going to impact Utah, Michigan, et cetera? And so what I think is that, there's been a lot of investment to address this market opportunity. It's in the trillions, right, for total transportation. So it's a big deal. And so they're trying to address that in software. Software has the highest profit margins. And so that's just like, number 1 way to be the richest person in the world or something, right? So that was sort of the dream and why everyone was pursuing this. And we're finding that, this is a lot harder than we thought, and perhaps you can't solve it with just software. That's what I think is happening. And so what I propose here and what I'm working on is you need infrastructure-based solutions. And, venture capital firms and companies in Silicon Valley, they don't want to do that. It requires a lot of work, a lot of government collaboration, hardware, which doesn't have as big of profit margins and stuff like that. It's sort of messy and harder and takes a lot longer, right? So it's sort of like an uncomfortable truth that we're realizing is, perhaps the solution is to work with infrastructure. If you have things that communicate with the vehicle directly, maybe that's going to actually get us to the point where we have vehicles that don't have a driver that aren't causing problems. Does that answer your question? It's a long time still. That's my prediction.
So I have a question over here on, you've looked at snow conditions, and I was wondering, have you looked at conditions like fog, heavy fog?
We have not, actually, but of course it's in the plan because, assuming that we can make major traction in snow and maybe hire some new people and stuff like that, then we would go after fog and rain. Maybe in the Northeast they get a lot of fog, in the South they get a lot of rain, and so those are opportunities there to address a need. We sort of envision that the technology we develop for snow could be translated to those other inclement weather cases. So that's sort of what we're focused on for right now. But the snow opportunity is sort of the most exciting. I'm I'm an avid snowboarder, and we like hockey and stuff like that. So the snow case is something that we feel we're uniquely qualified to try to address. But those other concerns are on the horizon, and we do want to expand to that at some point.
Well, thank you so much, Doctor. We really appreciate it.